So we have to show the analyticity of harmonic functions. Okay? So notation of yesterday were, so the theorem, let me state the theorem yesterday. So I will repeat the theorem I stated already yesterday. So let omega be open, u harmonic in omega, then u is analytic in omega. So at the end, the regularity result says that we start from C2 plus C2 minus Laplace of u equals 0. So u is C2. So we go to C infinity. And then we also go to analytic. So we have two steps here, analytic. Okay, so the proof, let us try to use the same notation of yesterday. So I fix a point that I call 0. And let me take d is this. I think that I use this. Check that I am using the same notation.
Yes, you use it.
And then I fixed r in 0 d over 2. Okay. And then we developed so Br is Br0. We developed Ux using the Taylor expansion with Lagrange remainder. It goes this minus alpha u0 x. And then I think I stopped at some alpha k or k minus 1. Let me check. I don't remember now the notation. K minus 1. Alpha equal k minus 1. And alpha equals 0. It's alpha equals sum.
Alpha factorial.
Or
Alpha factorial.
alpha factorial equals sum alpha equal k. So, and the claim is that we have to show, so for some psi, in BR. So we have to show that the limit, so for r sufficiently small, how small will be set at the end of the proof. So there exists r sufficiently small. Okay. For r sufficiently small, this converges to 0 uniformly. As k goes to infinity uniformly in yeah. So this is what we would like to prove. Okay, and let me recall the gradient estimate here. Let us try to write the gradient estimate. So we have grad alpha u less than or equal than sup u. Then there was, say, alpha is equal to k. Then we have the dimension this length of the multi-index, and then there was here the omega x to the k, I think. Okay? This was the gradient estimate. So we are going to use the gradient estimate to start with the bound, upper bound for this. So using, so also, okay, using the gradient estimate, we find, so what do we find? So we find the sum. So for the moment k is not specified, it's some k that divided by alpha factorial x to the alpha. So now I start to bound alpha equal k. So now I use the bound here. So let me call maybe C. Let me check C. Yes. So C is the supremum of u on the ball of radius r, or radius maybe d over 2. Sorry, or radius, yes, d over 2, sorry. I think we don't need the ball of radius r as a fixed constant. So then I have the sum. So now here I have the dimension n to the k, k to the k. Okay, now I can use, so the omega, so I'm working in, so this is the situation. So this is omega, this is x, this is d, and then I'm here, so small, even smaller, because take a ball of radius small r, and then here d over 2. So the distance from a point on the ball, psi is in the ball, somewhere here, say. So the distance omega psi is at least, is say, larger than or equal than d over 2. Okay? This is here. So 1 over the distance so we will use this to avoid problems with the denominator here. So we use this estimate with psi in place of x. Okay? Psi in place of x. So what do we have here? Okay, let me go step by step. So this is alpha factorial d omega psi to the k x alpha. So as I said, I use this estimate on d. So this is bounded above from 2 over d. Sorry, 2 over d. To the k. K is fixed. I mean, we will. So alpha is moving here. K for the moment is fixed. Then we will take k sufficiently. So this goes outside. And also n to the k, k to the k. Okay. Then I have alpha factorial factorial. So x1 let's see. Do you agree up to now with this? Is this okay? Okay, so now let me multiply and divide by the same factor. So constant 2 will be equal and 2 okay, factorial. So and I want to understand a little bit better this quantity here. Okay. So let's see what could be that object. So I seize this and I can erase everything. Okay. Maybe this. I can erase everything. There is no need to keep this. So let's see, for instance, what happens when n is equal to 2. Okay. So we have just alpha 1 and alpha 2. So we have alpha 1 plus alpha 2 is equal to k. So this means that alpha 2, say, is equal to k. Okay, and that object here, so this object here, becomes what? Alpha equal k. So we have k factorial divided by alpha factorial, actually, by definition, is alpha 1 factorial, alpha 2 factorial, which is in this case alpha 1 factorial k minus alpha 1. Okay. So this means that here we have alpha 1 factorial k minus alpha 1 factorial sum alpha 1 x2 okay. So this should remind you something. The binomial. Okay, so this should be sorry.
K.
This is k. So and we have x1 plus. Okay.
This one is also same as if we use induction is this we can do.
Exactly. So the idea now is to prove induction over n show that some k, remember here for the moment is fixed, because we are arguing at fixed k. Then maybe we will take k in some way, but here k has been fixed. So we could do induction over n here. So k factorial divided by alpha factorial x1 alpha 1 xn alpha n could be x1 plus xn, sorry, x1 plus xn to the k. Why don't you try to do this here by induction? So the first step of the induction has been checked. K here, sorry, n here has been checked for is okay for n equal to 2. So you have to suppose true for n minus 1 and then try to show it for n for n. It's a good exercise. Why don't you try here now?
Yeah, we need to divide first, we need to multiply k minus alpha n factorial and then divide. We need to multiply and divide.
So what I would do would be, suppose that I know the statement at the level n minus 1. I think it's your idea. So suppose that this is true. Suppose that 1 is true for n minus 1. And then one could try, of course, to write this splitting as so to use the case n equal to 2, no, here. This, why don't you try now this, so what should I erase? Okay. I don't know what, maybe there is sufficient. So you have to use the Newton theorem. So you call this is a new factor plus this. And then once you have this, then you can use the induction, the hypothesis, inductive hypothesis. Is it possible to do this? So maybe I can start. So I will use an index here. The index is convenient to call it alpha n. So alpha n from 0 to k. So I'm just writing the k factorial. Okay. And then I have x1 plus xn minus 1 to decay, and then I have
K minus alpha.
so yes, maybe to the alpha n, I don't know, I will see now what is convenient. It's the same, of course, xn k minus alpha n. Let me see if following.
If you change it.
Maybe it's better to do this. K minus alpha n and this alpha n. Okay. This is just the binomial k minus alpha n. Just the binomial. But for this now I can use the inductive assumption. Okay. use inductive assumption. So,
K minus alpha n factorial.
okay, so let me write the first part. Alpha n is an index running from 0 to k. So I have this, then I have, I'm just copying the first part. And I have xn the alpha n. And now I have to take my inductive assumption, okay? Where now in place of n, we're now in place of n we have this, okay? N minus 1. Okay, so I have just to copy this is another sum.
In place of k, we have k minus alpha n.
Maybe it's better here to write alpha 1 plus, no? Because this is the length. I would write this, maybe alpha 1 plus alpha n minus 1 now equal to k.
K minus alpha n.
Okay. Now this is there, sorry. It is equal to k minus alpha n. And written this sum. Now above I have k minus, now I have k, here I think I have, no sorry, where is my statement? Here. There. So now I have, in place of k, I have k minus alpha n here. X1 alpha 1 xn minus 1 alpha n minus 1. Then there is some denominator.
Alpha 1 factorial.
Yes, alpha 1 factorial up to alpha n minus 1 factorial. Up to alpha n minus 1. Okay, let me see if I did things correctly. Should be, I think should be correct. Right. So now let us do some division. Okay, so we can put everything with only one sum, just one sum. Okay, I think that this sum is just, since you see we are summing over all indices such that the sum is k, the sum of the just alpha 1 equal k. And then what remains here, I can cancel this with this. Ah, there is a factorial, sorry, here, I forgot, there is a factorial. What remains is just k factorial, and then I have alpha n factorial multiplied by this, which is just alpha factorial. Alpha factorial, and then I have, now we have the list of n x1 alpha 1. So this actually shows the inductive step. Okay. So if you agree with this, sorry for this long, maybe elementary computation. So let me copy what we want. So we have that this is less than or equal. Then this way. Now here we have x1 plus 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 xn2. Okay. So summarizing. Summarizing, we get what? Sum some constant here, another constant, k, n to the k to the k factorial. And here finally we have x1 plus xn. Now we are working inside the ball. So each xi should be less than or equal than r for any I from 1 to n. Because each x is in the ball of radius small r. So we can continue our inequality with this. We get here n to the k to the k factorial, n to the k, r to the k. So at the end, this is n to the 2k. Okay. C 2 over d k n the 2k k dk r to dk. Okay. I hope I didn't make mistakes, but so okay, so now we could use the, so let me call this AK. Now you see, this object here is independent of x in the ball, right? So it's just a number, just a numerical series. So in this sense, if we are able to say
That is convergence, we can find convergence.
I mean, if we are able to say that this, so if you are able to say that limit sk ak plus 1 is less than 1, okay, then the conclusion will follow. This is so-called the ratio criterion. Okay.
Ratio test.
Ratio test. Okay. So let's do the ratio test. So I divide this by this. So what do I have? Do 2 over d to the k plus 1 and 2 to k plus 1. K plus 1 to the k plus 1, 5 to the k plus 1, divided by k plus 1 factorial. Then here on the other hand we have n, sorry, we have the constant, it doesn't matter, so 2 over d k, then the 2k, k to the k, r to the k, and here we have k factorial front. Okay, let's see what happens. So we have, so this becomes 2 over d squared. Then we have n squared. So this is okay, this is okay. Now let's see this. Actually, r is just here. Then we have k plus 1. This is killed by this, and there is a k plus 1 remaining, which is killed by one of these. So we get k plus 1, if I'm not wrong, to decay. Okay? So this is equal to 2 over d n squared r 1 plus 1. So this converges to E, right? So converges. The only k dependence now is here. R has been fixed, n is the dimension, d has been fixed. So this is converging to 2 over d n squared r e. So it is sufficient now to take r so small, so it's sufficient to take r less than, so it is sufficient to take r less than 1 over e to d. So for r sufficiently small but positive, we get our claim. Okay. So because no, from this means this implies that this converges to 0. No, I have not written this, but since this number is less than 1, it means that AK converges to 0. So that AK converges to 0 for k sufficiently large. So and this is just a sequence, numerical sequence, independent of any point x or xi or whatever. Okay, as soon as r is sufficiently small. Okay. So this is the proof. You see, the proof requires actually computations. It was easy to say that from the gradient estimate one sees the analyticity. Easy to say, but the proof requires some work. Okay. Fine. So I think that this completes our study of regularity of solution of the Laplacian of harmonic functions. The issue of regularity for solution for elliptic PDEs is very huge and very difficult. So it's very interesting also, and there are various possible approaches to regularity theory. We just confine ourselves to the simplest non-trivial elliptic PDE, linear elliptic PDE. So now I want to go on, and I think that it's worthwhile to do something on existence. So because, you know, the aim, which is the aim will be, so given omega, say bounded for simplicity, open and bounded, Remember the initial aim of this course. Open bounded, given some G boundary condition, suppose that G is continuous at least, so that we can give a meaning to the value of G on an upper surface, at least it is everywhere defined. So the aim would be to find a solution, show existence and uniqueness open bounded, say connected, just to do existence and uniqueness suppose also maybe smooth. Existence and uniqueness of classical solution This is one of the interesting points. Existence and uniqueness of such kind of elliptic Dirichlet type, Dirichlet condition on the boundary. This means, so this is a classical way of posing the Dirichlet problem. What does it mean classical? It means that U is sufficiently smooth inside in order to define the PDE pointwise everywhere. Okay? But it is also, and this is a delicate part, it is also sufficiently smooth, say continuous up to the boundary, so that this boundary condition is considered in the classical sense. What does it mean, this? It means, say, for any y on boundary of omega, limit as x is in omega, say x converges to y of u of x must be equal to g of y. This is what we mean. So it is classical both the PDE, because this is C2 and therefore at any x this must be satisfied pointwise, but it is also classical the way we get the boundary condition. Pointwise everywhere, for anyone. Now uniqueness for this is not terribly difficult due to our discussion on maximum principle. But I will repeat it maybe. So this is the aim now, and maybe the best is, so in general there are various conditions on the omega that one should put, so maybe I think it's the best is to start with 2 dimensions. So we start with the case n equal 2, say, and omega is the unit disk d1 of 0. Okay, so just to see, so I would like to sketch, so in this case, we will not only show existence, uniqueness, we will see, but we will not only show existence, but we will give also a representation of the solution. So something more. Not only we are able to prove this, but we give a representation of U in terms of something. Okay, in this case, we will also have it's not really explicit. So not only smoothness up to the interior regularity, boundary regularity, but also, in this case, we will also have an explicit representation of the solution. Of the solution. So if you want, so we have a continuous function, which is say this one, continuous. And so we are in two dimensions. So it is, so G can be identified with 2 pi periodic continuous function on R. So in 2 dimensions, it is convenient to use the Fourier series. Okay. Okay. So G, I will use theta, I think. And from 1 to infinity. Okay, so we have the Fourier, so G is continuous, therefore we know that this, so define also the GK of theta for any k, define GK of theta Do you know the expressions of the expression of the coefficients? So G is 2 pi periodic. So do you know the expression of the coefficients? And then what? The expression of the coefficients.
This is the
Scalar product
scalar product
between
cosine,
G.
cosine and sine. And for
Huh? Comma. Sorry. Do you agree? Do you know these kind of things?
Yes, but I forget the coefficients.
Well, the coefficient, it's easy to remember because,
just multiply.
first of all, we isolate the constants, which is convenient to isolate constants. So this should correspond to n equals 0 here. Then the idea is that if we work in, let me conclude that and I will explain. So GK converges to G in L2. Minus pi times. Well, how to remember the coefficients? You have to think about this expression as a sort of expansion of any 2 pi periodic function G, expansion using a suitable clever basis. The clever basis is given by, well, there is a constant and then there are cosine of n theta, sine of n theta. Maybe you normalize by some constant here. And what is this? I mean, when you have infinite dimension, when you have a vector, usually you expand it in some basis, right? Finite sum. Okay. But what are the lambda? If this is an orthonormal basis of your vector space, when you have, say, a scalar product, an inner product, lambda, if this is an orthonormal basis, this lambda are, you know what are the lambda? Huh? Is the scalar product between V and EI. And this is the same. So we are taking the scalar product of V. Now V is a function, unfortunately, not anymore a vector, but this is a vector. We are working in this kind of space, or if you want, in periodic, no, 2-pi periodic functions. And in L2 we have a standard scalar product, which is H-K-D. Okay. So if you look at this way, you just remember that this is just a scalar product of our V with this element of the basis. Now the difficult part is to show that this is actually basis, no, of L2. The constant, I hope, is correct. 1 over pi, yes, is correct. Because I put the 2 here, right? So if you take, if this is 1, so I am integrating 1 over pi, and this, so I divide by 2 pi at the end, there is the 2. So now what I want to say is that usually we have that these are unit normals, and also they are, this must be 0 as I is different from J. No? So it's not difficult to check that. I hope with these constants here, these and these are unit vectors in L2. That the scalar product, as soon as n is different from m, then you integrate and you get 0. The difficult part is that this is a basis. It is a complete base of an infinite dimensional Hilbert space. And this is another story. I think that you did this, I don't know if you did this in the course of function analysis.
Yes, we did like example in Hilbert space. Of course, we give out examples and just.
So what did you do? I mean, did you work a little bit on this, or no? Just a very quick example.
Exactly.
Just quick example.
Just a
discuss like example and for example in L2.
We just give examples.
Okay, but you can go back to your notes on that course. So I think that probably the difficult part is to show that this is a complete system. It is called usually complete orthonormal system. Complete means that it generates all elements of the 2 functions like this, no?
Density.
Yes, it is a matter. These are infinite object spaces, so it is a matter of density. Well, I cannot do this now. But so this just you should know that we can have this. We can expand. Then we have these conversions. So the idea is very natural. So this is just the boundary condition, continuous 2-pi periodic function on R. So why don't we, so what is the very natural, so and we are looking for an harmonic extension of G inside the disk. We have something just defined here on the boundary, on this circle. This is G. And we want to extend this in a continuous way, because we want an extension continuous up to the boundary. inside in an harmonic way with the C2 function. So the question is, can we do this? And maybe you can guess what could be U. U of, say, R beta. Huh? Why don't we guess together what could be such an U once this is given G? Also recalling that
fundamental solution.
hmm?
We have fundamental solution.
No, fundamental solution, you want to use that. A fundamental solution is a solution in the wall of R2, which is singular, no? So that the fundamental, the fundamental solution, first of all, is singular at the origin, because it is a logarithm, no? And also, it does not fit in any case the boundary condition.
Convolve. Maybe we can convolve.
No, you should convolve the fundamental solution when you have problems of this sort. So if this is a suitable object, say a continuous function with compact support, for instance, or even a measure with, or even say a distribution with compact support, whatever, you can look for solution of this without adjusting the boundary condition. Without taking, you can just take the convolution of f with the fundamental solution. This gives you a solution of this. But you miss the boundary condition, of course. So maybe but here f is, this is homogeneous problem, no? We don't, f is 0 here, so
We need to search solution like just we need to change this a and t some functions, and this is like can you search in?
I give you a hint for this. So let me erase. This is clear now what we want to do. Be careful, because in my opinion, one of the most difficult part in this kind of problems and in the PDE in general is the boundary condition. Is in which sense we interpret this as, what does it mean this? This is classical, it's clear at any point this must be equal to this limit. We have continuity at any point this must be. But in general, one of the most difficult parts in PDE relies exactly in understanding how the boundary condition is obtained and to the boundary regularity of solution. Because we have studied interior regularity. We have said that inside omega U is infinity, actually analytic inside. What can we say when we go at the boundary? So that is another problem. It's the so-called boundary regularity. So now now this I can erase, sorry. This I can erase, this I can erase. So this was G. Yes. So these are the coefficients in this basis, in this complete orthonormal basis. Okay, now let me give you a hint. A hint is that if z is a complex number, z to the n does not depend on z bar, and therefore is holomorphic in the wall of. And this is, say, rho to the n. Writing it is in rectangular, in Cartesian coordinate is maybe not very convenient, but we know that we can write this, so we can also write and we also know that the real part and the imaginary part of these are harmonic. Fine. But you see, here, okay, here, let's work for the moment at finite sum. Well, this is very similar to this. There is something missing, right? And this is very similar. Parentheses. And this is very similar to that. There is something missing. So, what is the natural guess in order to define u of so put it r to the n?
In equal to b.
You look, I mean, how can we extend this expression? This expression is for r equal 1. You agree? We are on the boundary. So what is natural to do in order to extend this?
Multiply by r to the k.
Yes, or r to the n. Okay? So I think that the most natural thing to do is to consider Rn, In, Rn cos n theta plus Bn Rn sin n theta. This for any r 0, 1, for any theta, we say minus pi pi. Now, I mean, this is an infinite sum, right? But at least, if I stop at some k, do you agree with it, that this, if I cut the series and I take only finite number of terms from 1 to k. So let us define uk for any k. N uk a0 over 2. The coefficients are the same. Plus sum. Okay. And then r to the n cos n theta plus n r to the n sin n theta. So what can we say about this uk?
Boundary is equal to
The boundary is equal to
gk.
gk. Look, it's clear, no? We let r to 1 plus, to 1 minus. Okay. uk equal gk. Nice. And gk, of course, are continuous. Inside? Inside?
To be less than.
To be less than.
I don't-
Less than.
No, less.
Less than? What does it mean?
I mean, the UK will be smaller than G. The UK will be
No,
smaller.
I'm asking which kind of PDE this satisfies.
Okay.
And which kind of smoothness do we have?
I think it's harmonic.
Do you agree? It's harmonic?
Yes.
Because it's finite sum of harmonic functions. Real and imaginary part of z to the n. Finite sum. Not bad. Smoothness? The most we can hope. Surely C2 B1 and also smoothness up to the boundary, no? But even more than this. finite sums. So essentially, so you mean, do you agree that morally we have good compactness and closure theorems for harmonic functions? No?
If you inform.
So the point here is to pass k to infinity. To pass k to infinity and to get an object which satisfies this without k. Using our property that we already know about, this closure property of harmonic function, it's something like this. Okay, now you agree? So this is the strategy. So it's really not difficult, I mean, it's natural, maybe difficult to prove, but natural to imagine that this should be the unique solution of our problem. Now, uniqueness, you should be, maybe I leave you this as an exercise. So an exercise should be exercise. So so the problem, more generally, so let omega, so let omega be a bounded connected in Rn. Now I switch to the n dimension for one. Let n larger or equal than 2, comma, be an open connected, say, I don't know, C1. And consider then if you in C2, the problem has a solution, if there exists a solution, if there exists a solution to this problem, then such a solution must be unique. Then, so existence implies uniqueness.
I think if there are two, they concern the boundary. So
Let's see a hint for this. Okay. So then. Yes, then such a solution must be such a solution is unique. Okay, if this is so, and we prove that, so if we do some work, then this is the solution. The solution. Now, how should we the hint for that exercise? Yes, suppose by contradiction, usual argument in this kind of problems. So, suppose by contradiction, suppose hint, suppose by contradiction that U1, U2 are two distinct, not equal, are two distinct solutions to problem 2. This is problem 2. Problem start. Okay. Consider V, define V, U1 minus U2. Now we strongly use the fact that the operator is linear. So first of all, so V satisfies, then V is a solution to VC2 intersection C0 omega bar minus Laplace of V equals 0, no? omega. V equals 0 on the boundary of omega. As I said, it is crucial here that the Laplacian of the difference is the difference of the Laplacians. Linearity of the PDE. We start from the beginning. Okay. And now, what do we do? We have to show that V is equal to 0, so that we get a contradiction. So we need to show that V, to get a contradiction, we need to show that V is identically 0 now. So what do we do? Yes, we can use the maximum and minimum principles to get, so
Maximum and minimum boundary same, so it's
essentially yes. So we have that V of x must be, by the maximum principle, V is a subsolution, but it is also a super solution, so we have that this less than or equal to the max 0, max V and boundary. And the boundary of omega of V for any x. Huh? I think that this is
Yeah, for any x of omega, it happens the same.
okay. Now I would like to go back to this two-dimensional case to say something more. And so let me define HK G1 plus GK over K. So we know that GI converges in L2. No, sorry, we know that GK converges in L2 to G, right? Our theorems were concerned with uniform convergence, actually. Do you remember? Our closure, compactness, whatever. The theorem that we did was concerned with a different type of convergence. So maybe L2 is not... But there is a theorem that says something more about the means. This is called, I think, maybe Feyer theorem. Something like this. This improves convergence from L2 to uniform. So now it's also reasonable. So once we have this, it's also reasonable to consider the mean value of the UK. Let me denote them by VK. So what do we know about this VK? Well, VK is a finite sum, R in C2, E1, Laplacian is linear, is a finite sum.
boundary HK.
It is equal to G. So this we know. This we know. And now I leave you an exercise to you, which is, however, consequence of facts that we have studied, that there exists, that we have a sequence of harmonic functions. We have, now Vk is a sequence of harmonic functions, right? The boundary conditions are converging uniformly to G. And what I claim is that also Vk are converging uniformly inside Vk exists U harmonic, one in B1, such that Vk is converging to U uniformly in B1. Okay. Let me call this maybe not U but V.
Okay, here we still need to show that VK converges to U, right?
No, this is a part of the exercise.
Yeah.
Let me call this U harmonic. This is part of the exercise. Vk uniform U harmonic, Vk converges to U in B1. And maybe it's better to call this UV, because U was the previous one. Maybe this is related to what your comments. Okay, so U, V, sorry. So, and V is equal to G on boundary B1. Okay. What do you have to use for this? I want to go up to the boundary, so harmonic in B1 continues up to the this. So
Again, maximum P.
yes, you have also to use the maximum principle.
Vk minus V is the maximum.
Yes, you can bound exactly Vk minus you have to bound Vk minus its limit on the boundary. This bounds the difference inside, but this is uniformly going to 0. So from what we know, I think it's direct consequence of something that we have done. So the idea now is to show, so thank you for the comment, that V is equal to U. So idea, show that V is equal to U. So that V must be equal to our U, the sum that we have imagined at the beginning.
I think we actually proved I think this one, but I have a question. How we know there is this V? I mean, we can write F minus boundary HV, but it means looks like the same question, like if there is some function in boundary, so we can extend uniquely inside to harmonic.
No, I have not understood the question.
If we have a function in boundary,
Yes.
so some continuous function, so we can extend this function inside.
This is what we want to prove.
But
This is what we want to prove.
my question is just, is this V equal to U? We can show this one because
Because we have to show that Vk converges also to U. We have to show that Vk converges to U, not only to V, but it converges also to the same U. So that at the end U is equal to V. Okay. This is a hint. I mean, this is a hint because I will do this kind of result in a much more general case, any dimension. So I just want to tell you this in 2 dimensions, but we will go into all details in any dimension. So in particular, also this. Just let me conclude the case n equal to 2, which is very important, with another comment. So this was a hint. Another comment is the following. So quickly now, quite quickly. So if you substitute the expression of the coefficients inside, now I copy this. You have g of, say, phi enough plus, you should check this, I checked, it seems to be correct, rk cos k. Substituting,
This is u?
this is u. U is equal to v, by the way, so u of r, yes, u of r, theta. It's not difficult because you can recognize, no, the expression of the coefficients. You develop this, cosinus and sinus, and you get this equality. So see, this is a sort of explicit expression of the solution u based on a kernel that we want now to write in a different way, this kernel, and considering the values of u itself on the boundary. So in this sense, this is an explicit expression, but I want to simplify it, so let me call theta tilde equal theta minus phi as a notation, and I leave you to check the following, check at home. So these are exercises, and these are exercises. So check this list of equalities that I leave you. So home exercise. Maybe I used n before. Sorry, let me call this n so that for you it's simpler. N. Everywhere is n. Okay. Cos n theta tilde equal r to the n. This kind of some of these equalities are easy. So n for 1 plus infinity, r to the n plus 2, this is easy, plus r to the n, this is also easy, cos n theta tilde minus 2, this is it, this equality is immediate, it's just a multiplication, so plus infinity. Theta tilde, no, cos theta tilde, okay, this is just immediate. So now instead this is immediate, so I copy this and then I write this as minus sum and to infinity. And then I write this product in a different way, hoping that computations are correct, so you should check. So cosine n plus 1 theta tilde plus cosine n minus 1 theta tilde. And then the less easy equality is that there are several cancellations here. You write that there is several cancellation between this series and this series. These are two series actually. There is a cancellation of several terms up to the first and the last. Essentially, this turns out to be, if I'm not wrong, this. So there is this strange, now you will understand why I do this kind of list of intermediate exercise. Suppose this is true, then if this is true, this kernel here has another expression. So kernel is equal to 1/2 plus sum plus infinity up to the n cos n times p. It has an easy expression here, which is Rn cosinus, which is equal to cosine should be simply this, no? Because theta tilde is the difference, theta minus phi, so it's just that ratio, okay? So I copy 1/2 and then I take this divided by this, okay? Plus minus r squared plus r cosinus theta divided by r squared plus 1 minus 2 r cos theta theta.
Is this a Poisson rule?
Yes, yes, exactly. So now I put all things together, and if I just copy, so check also this equality here, 2 r squared plus 1 minus 2r cos theta tilde. So I do just only one denominator, and I get 1 minus r squared. Okay? So this is a tricky way, very tricky way, simply to replace this square parenthesis with something more easy to see. It's very tricky, but at the end, what it is inside parenthesis is nothing but this. If this is true, now I can substitute and give you a sort of explicit, say, expression of u. So at the end of all this computation, please check and check the details, also what I've said about VK, UK. It is a classical exercise. I don't know where it is, but it is a classical exercise. A classical, notice, it's not an exercise, it's a classical theorem on harmonic extension from inside to the disk. I think that in the book, Wildebrand, you should be
They
there.
use it like it's easy to see
Ah, sì.
that, like, and they put some of the details, not everything.
Okay, I cannot tell you the reference, unfortunately. So I can continue. So, and as you said, you said the Poisson process. So at the end, this is equal to 1 over pi integral. But there is maybe some constant r. So we have 1 minus r squared divided by 2 pi integral minus pi to pi g of phi divided by r squared plus 1 minus 2 r cos theta minus phi d phi. And this is u. This is the solution. So we not only have that it is harmonic inside the continuous up to the boundary, but it is also has a more or less explicit expression using its value on the boundary only. So it is like, you have to think about this as a sort of mean value surface mean value property, but the surface mean value property was something telling you that the value at the center was something that you can deduce from the value on the boundary of the disk, but at the center. This formula says that also the values out of the center can be deduced from the value of u, which is g, on the boundary, but divided by something on the denominator, some sort of kernel. And this is called the Poisson formula for the disk in 2 dimensions. Maybe this is called the Poisson kernel also. This is a strange way to write.
This is a convolution of G and Poisson.
Exactly, but you don't see here the convolution, but usually the way to write it is to write a norm of a difference. We will see, we will see. In any case, in 2 dimensions, this should be the Poisson kernel. Okay? Well, it would be nice if you, so you still have to tell me about the exercise on harmonic polynomials. You still have to tell me what about uniform approximation of harmonic polynomials in any dimension to a harmonic function. And please look maybe in the, or do by yourself the computation, fix the details of this 2-dimensional important case of Poisson kernel using the Fourier transform, the Fourier series. I think it's very classical, but maybe it's better to start from this before going to the n dimensions. So the next week, tomorrow there will be no lecture, I think. So the next week we will do the same in any dimension. Not the same, no, it's not the same, it's another story. We do this and start to study the solvability of the Dirichlet problem on a ball in any dimension. So at least for the ball, I hope that at the end of this course, at least of the ball, for the ball, we will find a unique solution for continuous boundary conditions, at least, just continuous.